last but not least, I'd like to show you how Mathematica makes such quick work of what we're trying to do here at first, and then how we will use Mathematica to generalize this process to repeat it many, many times. I'd like to remind you, here's our graph with our very small example of just a little 3x3 simple town. And what we want Mathematica to do is to come up with a walk on this graph, let's say starting at vertex 1. And then we want to pick of those cells that are adjacent to the cell 1, we want to pick one that's connected to walk in that direction. From there, we'd like to randomly pick to move from this spot to somewhere else that is connected to this spot without backtracking. And ultimately, what we want to do is visit every vertex of this graph exactly one time, so no backtracking, but we need to visit every vertex. And that will give us a little path that walks through the graph. Now, it just so happens that that's a thing that mathematicians have been interested in for a long time, and such a path in a graph is called a Hamiltonian path. And Mathematica has algorithms for determining those when a graph is input into the system. So Mathematica has a command called find Hamiltonian path, and as input it takes a graph, and then it will output that path. So let's create a shortcut for this graph right here, and call find Hamiltonian path of our graph. And there it is. Mathematica has said that the Hamiltonian path should have this form. And if we'd like to visualize it, we can. We can ask Mathematica to draw that for us in our graph with highlight graph, where we need to pass in the graph first, and then we need to pass in the path second. Our path is the output of cell 56, but let's cast this list of values as its own graph in order to have the highlighting look really nice. And we can add some vertex labels to it if we'd like. And here we go. 9, 6, 5, 8, 7, 4, 1, 2, 3. It shows us precisely what that path is going to be. If we take this path and translate it back into our Excel document, let's just take the first three values, 9, 6, and 5, and make them into a district in our 3x3 grid. Let's take 8, 7, and 4 and turn them into a district, and let's take 1, 2, 3 and turn them into a district. So going back to our visual in Excel, 1, 2, and 3 are a district, 9, 6, and 5 are a district, and 4, 7, and 8 are a district. So this is the random collection of districts that Mathematica has given us. Just as easy as that from this Hamiltonian path. So we've seen how Mathematica can very quickly and easily read in our data from a CSV file and find an answer for our districting problem. It can create these districts for us through this find Hamiltonian path command. The problem is that Mathematica uses an algorithm in order to find that. So I can come back up here. If I wanted Mathematica to repeat this process, I could think that I might be able to come back up here to the find Hamiltonian path command and rerun it, and everything would work just great. However, Mathematica is using an algorithm in order to get this output. So when Mathematica does this command again, it's going to give us exactly the same output. So there may well be many Hamiltonian paths from this particular graph, but Mathematica is only going to find the exact same one over and over and over. So if we want Mathematica to find a different Hamiltonian path, we're going to have to be a little bit more clever. And what we're going to do is we're going to use a little bit of randomness, which is also built in very nicely into Mathematica in order to accomplish this. So what I mean is, when we were in Excel and we were putting this numbering scheme onto our little 3x3 grid to create this adjacency matrix, we put the numbers in a procedural way in order to create some Python code that could output this large adjacency matrix over here in a very easy way. However, we could have labeled these 9 entries however we wanted to. If we really felt like it, we could have done something like 9, 4, 2, 1, 7, 8, 5, 6, 3. And that's a perfectly acceptable way to number these things. I did it randomly, so I couldn't really communicate that to Python, this structure to Python, but I could have done that. Now, we would still want to create an adjacency matrix that relays the same information on who's connected to what. And if we did this random numbering of these cells and created an adjacency matrix that encompassed this relationship and did the whole process of exporting that and importing it again, if we entered in this numbering scheme to Python, it would put out a different collection of things for the Hamiltonian cycle. So what we need to do is mimic that from within Mathematica. We need to have Mathematica shuffle these vertices while keeping exactly the same relationship. So there's actually a shortcut to doing this directly within Mathematica that will shuffle things for us so that we can run this fine Hamiltonian path function again on what looks like a different graph, but really conveys the exact same information. So let me show you just how that works. And let me show you with something that has more than just zeros and ones in it so that it's a little bit more clear. So I've created a 4x4 matrix that I called test here, and I've displayed it in its matrix form. So it's got the numbers 1 through 25 here. And here what I've done is I've created a list called ORD. And what ORD does is it has a random shuffling of the numbers 1 through 5. 1, 4, 5, 2, 3. Random ordering of those 5 numbers. If I create this list and then go to the test matrix and I access this list twice, look what happens. What I've done is I've taken the test matrix and I've told Mathematica to put the rows and columns of this matrix in this particular order. The first row will be in the first spot. The fourth row will be in the second spot. The fifth row will be in the third spot. The second row will be in the fourth spot. And the third row will be in the fifth spot. And I'm going to do that for both the rows and the columns. So I've done this to my matrix. Now let's go ahead and let's do something similar to that with our trial matrix. So I've created here something called perm1, and let's ask the trial matrix to shuffle according to perm1. Now the perm1 I've created is very simple. It just takes the second and the fifth rows and columns and it wants to exchange them. We set perm1 and then we ask for trial rearranged according to perm1 to be shown in matrix form. And what we have is displayed right here. And it looks a little different than our original trial matrix did. Now let's ask Mathematica for the adjacency graph of this new matrix. In terms of its picture, it looks exactly the same. Let's have it add some vertex labels. Notice that things actually are a little bit different. Before, 1 was connected to 4 and to 2. Now, 1 is connected to 4 and 5. So you can see that the overall structure is exactly the same, but the numbering scheme is different. So if we can use that to our advantage, we can find more Hamiltonian paths in these renumbered graphs that are equivalent to our original graph, and we can use that to find different numbering schemes, as we'll see next.